Okay, so the last, there are so many other, I will mention more names of the topological indices, but the last one that I want to share is the Harary Index. Okay, after the class, maybe to complete the background of all the indices, I would suggest that you would do some literature review. Google, nowadays is very easy, right? Zahida, during my student time, I really have to go to the library, find books, even to connect to the internet from my house, I have to dial. Okay, now it's connected to the school. So we don't have WhatsApp, we don't have that, all those things many years ago. So nowadays, use that opportunity. Google about all these name of the indices, they came from the person who introduced them. At least we know more about this than just during the class, okay? So again, we have for this Harare Index, we need to have gamma to be a connected graph. And we want the vertices to be 1, 2, until n. Okay, so the Harare Index, H, or normally they just use this, or you can just write like the Harare Index of a graph, gamma. But sometimes people just put H. It's a half, okay? It's a half sum of the sum elements, okay? D to the Rij. Again, we want the index to be from 1 to n. But I have to, what is this? This is not just the distance between the two, there is the R, right? So the Rij is actually the reciprocal. In Malay, we call it salingan, 1 over. Reciprocal, you know, 1 over.
Balikan.
What is it?
Balikan.
Balikan.
In first,
Salingan, balikan. Reciprocal. All right. So this is 1 over the distance. Shortest distance there. Yeah? When I mentioned about the distance, is actually the shortest distance. If they are not equal, because if it's equal, it's 0, right? You cannot do 1 over 0. So you just put equal to 0. Okay. So this is the normal distance. It's 1 over. And so I had to pull the whiteboard from before and draw that graph. Okay. By now, you must be remember already about this graph. System graph. 1, 2, 3, 4, 1, 2, 3, 4, 5. Okay, so this is just a simple connected graph, and we want to calculate the Harare Index. Okay, so it's equal to that. All right. Okay, so H of gamma is equal to 1 over 2. I from what to what? 1 until 4. Yeah? 1 until 4. Okay. So how many times, Nidia, we want to calculate this? 4 times 4. Right? 16 times. Okay. Add up 16 pairs of IJ. All right. Okay, so if you want to write out, that will be, for example, the first one will be 0 plus 1 over 1, 1, right? 1, 1, 1, 2,
1, 3,
1, 3,
1, 4.
1, okay, plus
2, 1,
2, 1,
then 0, and 2, 3.
2.
Oh, okay. Mm,
Then
still continue. 3, 1, 3, 2,
3, 2,
0,
0,
and 3, 4. And then the last,
4, we can do 4. If it's 10, I'm not going to do 10.
yes, just etc.
For first one, it's okay. 1 of D, for 1,
For 1,
D, for 2,
for 2,
D,
for 3,
3, for 4, you don't do, you do.
0. Okay.
Now the distance, you can plug in all the distance. Yeah. Let's try not to erase. Okay. 0 plus 1, right? The distance from 1 to 2, 1, 1 to 3, 1, 1 to 4, 1. So you imagine if it's complete graph, right? It's all ones.
All 1.
All one. So you can easily get it. Then the second one is 2, 1, 0, 2, 3, 1,
1,
2, 4, 2.
1,
2.
or 2, yes.
There is not only one, because if it's not connected,
Oh, it's gonna be 2.
yeah, it's not connected, then it's 2. The others, they're all connected, right?
Yes.
So you will only watch out the 2, 4 and 4, 2, right? So you see the others, they are all ones. So you can go do it quickly. You don't have to do it like one by one. You just look at the only one that is this missing is the one you have to do 1 over 2. All right. So that will be the same thing, and you have 2 of this, right? You have 2 of this, you have 2 of this. Okay. So you will get this. Okay. I can do shortcut, yeah. Right? So this one is 6. This one is 5. Right? This one is 3. 3 times 2 is 6. This one is 2.5 times 2 is 5. 6 plus 5 is 11. So 11 over 2. So this is the Harare Index for our particular graph. All right. Now we have to find the Harare Index of the 3 graphs of the 3 groups. Okay. So in this lectures, we have found 3 times 3, 9 times all the indices. Wow, that is like so many results. All right, let me write down, and you can see it contains some kind of fraction. Yeah, from before you see they're all like just distances. They're like the number of degree, which are all integers. Right now, because it's the reciprocal, kebalikan. So that's why you see some fractions in this one. Okay, so I call it theorem 31. So H of the non-commuting for the right when n bigger or 3, non-commuting. Okay, this is equal to, I write down here, it's longer, 1 over 4 7n squared minus 9n plus 2 and on 1 over 4 7n squared minus 16n plus 6 and you see why we get this. That is from the 1 over 2. Then you combine and so forth. So the non-commuting graph for the dihedral group need to be break up into 2 cases, and that is why we get this. So we have the case for the odd one, it's the multipartite graph, right? So you will see for the from proposition 7, I believe. If you remember, I write this last time. There is the n times of this. And the one n minus 1. So we have the independent set n minus 1. They are not adjacent, right, to each other. And we have n independent set, only one element. So we have the number of edges in the proposition. After that, proposition 10, we have 3n n minus 1 over 2 edges. This one with distance 1. Okay, this one is with distance 1. And we have n minus 1, n minus 2 over 2 with distance
2.
2. So the reciprocal is 1 over 2. The reciprocal distance. The distance is 2, but 1 over 2. And the Harare index you can find by adding up the number of edges, and particularly you add this up with this one, yeah? Then you get to this one. So it's pretty straightforward for that particular one. For the other one, for the case n is even, the graph is still multipartite, but this one is 2, 2, 2, and minus 2. So similarly, you have 3n n minus 2 over 2 edges with distance 1. This is n minus 2 for this one. Then n minus 2 and minus 3, right? With reciprocal distance 1/2. So you add up all this reciprocal and you will get exactly this. So this mainly come from the fact that the non-commuting graph of the dihedral group is multipartite. Okay, so you understand how the graph is and separate and find the edges. For this one, I think it's much simpler than the index before, in which you have the n1 and n2. That's pretty complicated, right? Okay. Now, for the next theorem is the Contiguous C class graph. Right? The Contiguous C class graph when n bigger or equal to 3 and is 4k. Then we have this is equal to n plus 2 over 8. Right? Okay, now why we get this? The conjugacy class graph of the dihedral groups in the case n and n over 2 even is complete. Okay, so this is a complete graph of n plus 2 over 2 vertices, right? So since it's complete graph, the reciprocal distance is just the distance, right, between the two vertices, right? So by definition of the Harare index, we have just the distance. So we have how many? N plus 2 over 2. I'm sure, Nidia, you will remember after this how many edges when you asking about the complete graph, right? So you see the formula becomes the formula for the winner index because the d to the r of ij, which is 1 over the distance is, if this is 1, right? It's a complete, the shortest distance is 1, it becomes the same, right? It becomes the same. So it's similar to the winner index because it's complete. All right. Now next is the Harare index. Just now it's 32. Missing number, theorem number. Just now it's 32. Now it's 33. Right? We go to the co-prime. Okay. So still for the dihedral group, and n we go equal to 3 and odd. Okay. Now this is equal to 3n squared minus 1 over 2. All right. The next one is when we have two cases, right? This next one is for the case n equals to 2 to the k. Okay, this becomes theorem. This is n plus 1 to n minus 1. So you see the half everywhere because of the formula of 1 over. Okay. Now, if I ask you to prove this, then you know the step already, right? You look at the graph, then you look at if it's multiplet, it's like this. If it's complete, it's easy. Don't write easy in the proof. Because sometimes students write the proof is easy. No. Okay, next is the non-commuting for the next group, yeah? Theorem 35. Non-commuting for the generalized quaternion. And this is out to be 7n squared minus 8n plus 3 over 2. Okay, this is for order 4n, n bigger or equal to 2. All right. Now theorem 36. This is for Contingency class graph of generalized quaternion. For this one, we want non-commuting. I have that. Okay. This is for Contingency class graph for generalized quaternion group, and bigger equal to 2 and even, yeah. And this is equal to n plus 1 over. You see, if you put together all these different kind of indices for this different kind of graph for these groups, you will see some similarities because in some cases the indices are the same for some graph because of the formula, right? Just now, as I mentioned, for complete graph is like this, and the summation, double summation becomes equal because the distance becomes equal for the complete case. Okay, the next one is for the generalized quaternion groups. For the case n2 to the k minus 1. Okay, for the co-prime graph. For the co-prime graph. So H of co-prime graph for the Q point. So 4n squared plus n minus. Now, how do we get to this? The co-prime graph of the generalized quaternion group is a complete bipartite graph. Okay, so the co-prime graph of the generalized quaternion group is the complete bipartite graph. And this is the edges. Okay, for this one. So we have this many independent set of vertices. They are not adjacent to each other. So this is actually we call earlier as a star graph, right? So the star graph, the complete graph, you can show this in general, in which which one of the vertices they are all equal to 1 is the when you put what is it, n is 2 to the k plus 1 vertices, right? 2 to the k plus 1 minus 1 is the number of 4n minus 1. Okay, the generalized quaternion group of this one. So you have the number of edges with the distance is all 1, and then how many with reciprocal distance 1/2. So you can add up the number of edges for that particular one plus the reciprocal distance. The one that I give is also quite direct in the proof that I give in your notes. So you can figure it out from the star graph. Okay, now next would be the non-commuting graph for the third group, quasi-dihedral group. All right. So we have the last one. 38, 39, 40. Okay. So for this one, we have to change the QD to the okay. The first one is the non-commuting one. Okay, this is 7. Yeah, quasi-dihedral is quite complicated. 2 to the 2n minus 4 minus 2 plus 0. Okay. For this one, when we have the different little bit, right? The condition and with order, yeah, n bigger to 4. Okay, this is 2 to the n minus 3 This also highly dependent on the graph of this one. You see 1/2, the distance. Some of them is 1/2. They are embedded in 2 to the minus, right? Because you don't see it, but it's inside the negative here. Okay. And then the third one, all right, the third one is, I'm missing the graph in the name. You can add the G in the graph. The Harare Index of co-prime graph for QD2 and theorem 40. Yeah? So this one is equal to 2 to the 2n minus 2 plus 2n minus 2 minus. Okay. Let me just give the proof of this one because we have the time. Okay. Okay, I have to refer to the proposition for the co-prime graph. The co-prime graph, if you have your notes, go to proposition 17. Proposition 17. From proposition 17, the co-prime graph of the group G, considerable group, is equal to the complete bipartite graph 1 to the n minus 1. Okay. Then there are, okay, for this one, an independent set of the identity element of G for this one, and an independent set of 2 to the n minus 1 vertices, okay, which are not adjacent, right? Okay. So this one is actually the star graph, right? Sometimes we call this star graph of 2 to the n vertices. All right. Okay. Hence, it has 2 to the n minus 1 edges, okay, in which the distances of all vertices are 1. Right? So there's one set in which this is like a complete one, in which vertices, and then there's another one, and there's another one. So you have this many. Meanwhile, there are 2 to the n minus 1 times 2 to the n minus 2 over 2. This one has to ask Nidia how I get this formula from the complete graph, which have reciprocal distance half, right? For the complete graph. Therefore, now we want to calculate h of the coprime graph of q d n equal the number of these edges of this q d n. Just add that up to this, right? 2 to the n is 1, 2 to the n is 2 over 2. So you can plug in, we have 2 to the n minus 1 for this number of edges plus 1/2 of this whole thing. And finally, simplify, then we get 2 to the 2n minus 2 plus 2 to the n minus 2 minus. So this is how you get the Harare Index of the coprime graph of the quasi-Dahiri group of order 2 to the n. This is actually directly by using the definition. So you see, you can come out with a general formula without even probably referring to literature review, although it's already there, right? What is the Harare Index of the complete graph? Okay, before you refer this, I'm sure all of you can now think of how to prove and calculate or compute some simple index of certain graph in general. Like for complete graph is like this, for star graph is like this, right? Okay, so I want to share a little bit about, this is what I want to share, Bu Zahida, about the topological indices. Not only the topological indices, but I have also shared different type of groups. Like Nidia said, you have not really studied about this in particular, right? Dihedral group, yes, it's very common. Quaternion also, I saw Dr. Intan, Bu Intan already mentioned about the generalized quaternion, also with the presentation of the group. But this one probably is not that familiar. And there are many others. So there are many also future works that can be done to find. Let me see. Let me write here. Actually, yesterday, I think, Zaida, or this morning, I cannot even remember. I mentioned if you want to collaborate, right? If you have someone, if you are from Airlangga, your docent is here, some of you, we can actually collaborate. And I can become like we have, like in UTM, we have external co-supervisor for our students.
Oh.
So maybe I have a student coming with me. I can say, okay, why don't you co-supervise with Zahida from there? Because before, like Dr. Ayu here, she has an external co-supervisor. You know Prof. Ahmad Irfanian, right?
Yes.
From Ferdowsi, yeah. So he's actually Dr. Idayu's external co-supervisor. We can do that. We have from Airlangga, we have from Gajah Mada, we have from, so this kind of collaboration that we can do. And a good thing, if you remember, I shared about the mobility activity in UTM. I had quite a number of students who come here for 1 month, 2 months, 1 semester to just do short research attachment. At least you can become, you are like Airlangga student, right? You can just come, and because we are partners. The one that I share with you my slide. Oh, I will pass you the slide, Ibu Zahida. You can pass to the students the slide about UTM. The one that I upload is all about the notes. The one about introduction to UTM, I will pass later, or I will pass to Ibu Zahida. It's not part of the topological indices. That's why I didn't put in the. But this is something that you can do also. You can come and be our UTM student for a short while, right? At least you can travel abroad, hopefully next year, really when it's safe to travel. If you don't get the opportunity during your study, when you become a docent yourself to all these students, you are still welcome. If you need to go to any other universities in Malaysia, I'm part of also Malaysian Mathematical Society. So I can connect you with whoever from other universities in Malaysia. Back to this work, okay? So I mentioned about just these groups, right? You have many others that we haven't even looked, many others for groups. There are many other type of groups that people have not found the graphs, right? So this is what you can extend to the same graph, the same 3 graphs for different groups, or come up with a new graph for these 3 groups, right? And there are many other topological indices. Okay, political indices that have not been computed for other graphs of groups, yeah, because the one that they compute is all the graph that they have from the graph theory, right? So this one, there are other, which is called the Prendick index. Okay, Dr. Ibu Zahida, you mentioned about the project you have. Which index is it?
You already talked about it.
One of these, yeah. Okay. Charles index, we have this. We have degree distance index. We hope actually to come up with a new index, but it didn't get to it so much. So if you think like, why don't you create this new formula to, like, we have already the reciprocal, we have the square, right? Who knows, maybe there are others, the cube and some others. So this, from this, you can also find some properties of these indices. What are probably in general formula for the maximum or minimum value, something like this, yeah, for this one. And you can make your group larger, right? For these groups, why not, if you have G and H, 2 groups from whatever groups that we have, why not we try with the direct product of these groups, right? It becomes larger. What happened to the graph? And with that particular graph, whether it's connected, if it's connected, then you can probably find the topological indices. So these are just some other things that we can do, but to make sure you do the background check if people have done it or not. So these are just to give some ideas about further research that you can do. But I think I already give you just the basic, like we learn in class, you learn about groups, you learn then, but what is actually research, right? Research is something that nobody has done. I mean, the novelty, but based on whatever results, whatever the literature review that people have done, these are the steps. So by giving you some examples, you can see the pattern. So it's always coming from this group. You got this graph, and from the form of the graph, you can compute all the indices. Some of them you can say that it's probably very, very similar. Some of them computations are different, but once you get used to it, you get used to the definition of different indices, then you have the idea of computing. I don't say it's really difficult or cannot be done. Yes, it can be done. The first time, I'm sure whoever is doing research is very, very hard. You imagine the one that I give you when I give you the definition, like what is N1, N2, right? Now, giving example, it's getting me. You just imagine if you have to sit at home and you have this one paper you try to understand by yourself. Or you come to class like this with the whiteboard and then you do this together. Okay, so Ibu Zaida, that's it for my lectures.